Welcome everyone to the lab 5. Um, this is sort of an extension from our last lab, which was about familiarization with ADS. We have learned a little bit about the ADS, little basics about the software, especially in the context of the transmission line and its mixture. So I'm not going to be covering a lot about basic things and basic operation of ADS, assuming that you have done those things successfully in your past lab. So to begin with, in this tutorial we are having initially, if you look at the tutorial, uh, there are some quite a bit of theoretical part, uh, and which in fact you have already seen in your theory classes, or maybe you'll be seeing those soon in maybe one or two classes, within a couple of classes maybe. So you see, as you go forward, there are some transmission line basic things, those telegraphers equations, traveling wave equations, um, propagation constant, and also there are some concept about traveling wave things, impedance, and reflection coefficient, so, and VSWR as well. So I'm assuming that you have already, it has been already covered in your theory class, and in fact we are going to skip those parts mostly because of that thing. So maybe we can jump straight into the lab content today, which is you can see at page number is 9. So let's start from here. Again, if you're having any questions about those theoretical parts, even after having the classes, you might ask me. Maybe we can figure out to clarify those things for your understanding. Okay, so let's move on. Well, if you can remember from your past lab on ADS, I think you remember this circuit, how to build that circuit and how to run the simulation and how to look into those parameters called S11, S21, and Smith chart from the ADS. Those are pretty straightforward, as I believe. So, from that circuit, as you can see, at the very beginning, you see a question that you should answer in your lab report, that provide a plot of S11 versus frequency and a Smith chart for resistor value equals to 176.5 ohms. What does it mean? So, well, since this is an exercise question for you, but let me help a little bit with that. You see, if you remember the previous circuit, all you have to do, you have to change the terminal 2 here, just change the value. Then those things, you just keep all the things pretty much unchanged. So just put the value here, which is 176.5, and let's see what happens. Okay, the thing is up to you, and let me know if you are in doubt when answering this question. I can definitely help. Okay, so other than this, don't change anything. As I said, that is the correct input impedance, which is Z 50 ohms. Don't change the transmission line parameters. See, Z is 86.6 ohms. That's the electrical length, which is 90 degrees, and the operating frequency is going to be 2.5 gigahertz. However, here you have to be looking into the things at 1.5 gigahertz. I'm assuming that you know how to do those things if you just have followed previous tutorial. Alright, so now we are gonna be playing pretty much with another feature called Smith chart matching, and that's really a kind of cool feature in areas, and I like this very lot, and you will love it, I guess, because it's pretty easy. It's just a piece of cake to to match any transmission line. It's sort of an automated thing. You don't have to draw the circle. You don't have to use some geometric tools which you have done in your Smith chart process. The areas will do the things for you. This is really cool. So you'll get to know that in a moment. Okay. So okay, let's get started with the areas, which I've already opened that. So for these, you have to search for a new thing, which is called Smith chart. Oh, before that, you have to open. Okay, you have to construct a circuit before that. But let's get this done first. Okay, so let's follow the tutorial. So just in the palette list, search for Smith chart matching, which is already there. Press enter. That's the one. Just ignore this. Press OK here, and that's it here. So this is another component. In fact, this is the matching network, equivalent to matching network. So okay, just please note, this is just it's just a matching network, but this is not a complete circuit. As you can see, the two terminals are open. We haven't added anything. So from your theoretical class, as you know, that normally we are matching between source and loads. So that means there should be a source in this side and there should be a load in this side with any arbitrary impedance, and we can put this matching network right in the middle to match the things. Okay. So for these, to construct the matching network, you have to go to the tools and press the Smith chart. This gives you two options: update Smith component from Smith chart utility, or update Smith chart utility from smart component. So we will be going for the first one always. Okay, I was doing something, so let's delete those first. Let's reset everything. Okay, so this is our Smith chart utility, just to construct the matching network. So there are some introduction here. If you look at the tutorial, okay, let's zoom a little bit. Okay, so this is the component palette again, and this is the Smith chart area. Okay, and this is your network response. You can see this parameter here, or yep, for your frequency of interest. This is the normalized situation. Normally, you know, whenever you are doing the calculation for Smith chart, normally we have to divide all the impedance by 50, which is characteristic impedance. So the ADS will do that if you just check on that thing. Okay. This is the network schematic, which is you see is the source one. Okay, and which is normally 50. That's the load. We'll change that thing, or say just anything that could be anything. Okay, so let's put 50 here also. I'm assuming this is completely matched, and you see there are different colors and different circles. I mean, this is the Smith chart actually, but you see this is our 50 ohm point. That means there should be a That's the unit circle here, and this the admittance circle. You can choose all the things from here. If you don't want to see the admittance circles, just click on that thing. If you want to see only the admittance circle, not the impedance circle, just click on that thing. And you can set more if you like. Let's say go to view chart options. If you want to see only resistance and nothing else, you can click here. If you want to see just the reactance, not resistance, that's here. That's a very kind of cool feature, because normally we don't want to see too much of crowd in this feature. In that case, this feature is really important and really beneficial for you. So right now at this point, we want to see everything. Okay, let's get forward. And okay, so let me show something else. You see, there are some values here, reflection coefficient thing, that the VSWR, the ideal is always 1, because the load, both the load and the source are 50 ohm. You see, both of them are right at the center of the unit circle. That means those are perfectly meshed. That's the operating frequency, the frequency of interest. That's the characteristic impedance. Okay, so if let's see how that changes across the Smith chart. So let's say we are locking the source impedance at 50. So okay, so let's lock it here. That means we don't want to move that accidentally. So now you see, you can change, you can move the load point anywhere, okay, and the value is changing. You see, the value is here changing, this VSWR is changing, but you cannot change the source point. You see the caution that ADS will not let you to change the thing. Okay, so either you can change the position here, just click on the mouse and holding these things and just hovering across the Smith chart anywhere, or you can put it here. Let's say 150 plus J asterisk 60, and look at the value here. Just click somewhere here, and that's it. That's the value. So still, see, if you change it, so sometimes we accidentally change it. In that case, you want to stick to 150 plus J asterisk 60, and you don't want to change that. In that case, you lock the things. So that means it will never be changed. So for now, we have locked source impedance at 50 and load impedance at 150 plus J60. I put it because in the next step, we are going to build up a matching network for this circuit, okay? Because it's clearly not meshed. This is here and this is here, so we have to match it so that this point, we have to start from this point, and we have to come to this point. So that means that is what you do when you solve this Smith chart. Okay. All right. So let's get forward. I think we have covered this. Okay. There are some introduction of the palette. Well, as the picture say, this is, if you just hover your mouse, it will say itself. Okay. You see, normally we need that series inductor, shunt inductor, capacitor, line length, about short stop, open stop. Okay, so nothing much here. We have talked about these things: chart options, loading the things, and locking load impedance, locking source impedance, low. So yeah, you see there are some basic things here. I think that would be better if you just solve a problem straight away. Okay, so you see these things are easily covered, will be covered in our next stages or next steps. So let's do that. Okay, so don't worry. Now, if I didn't skip this part, but the thing is that if we solve this part, this is going to be solving these problems as well, and we don't have to answer anything from this section. So this is just kind of like introduction, how to add the things and how to build up a network, impedance matching network. Okay, you are going to see those things in a bit. Okay, so let's start with the problem. Assume the source impedance of an electric network is 50 ohm, while the load impedance is 150 plus j60 ohms as shown below, figure 14. Design the matching networks at the frequency of 1.5 GHz. Then simulate each network in ADS by adding suitable terminations and plot the S11 and S21 curve. So if we solve these problems, as I said, this is going to be covering all the things that we have skipped right now. Okay, so don't worry. So let's start. Let's construct this circuit first, which you have done in your previous lab. Let's do that again. So we have to use a terminal with, right terminal with characteristic impedance of 50 ohms, and we have to build another terminal at the right with 150 plus j60 ohm. We have to build up two ports at the both ends, and we have to put the things right in the middle empty for now. Okay, so let's delete this. Let's start fresh. If you want to put a terminal, you have to go to the S parameter T line ideal. Nope, sorry, that's gonna be S parameter things, and just click on that thing. We don't want more because we want more actually at the right. Yeah, so this is gonna be 50, but based on your tutorial, this is gonna be 150 plus j60. Just type it in plus, and always remember, if the syntax is not right, the ADS will give you warning that that's not right. So whenever you are trying to type impedance, type J, then put a status, no gap, nothing, no space, just J times 60. And as always, we have to put two port at the both ends. You have to rotate this, Control R. We have to connect those things. As you can see, those are reds. So done connection and put ground here. Okay, so to stop here, we are not completing the, sorry. There you go. So so clearly you can see that this network is not matched. 50 versus 150 plus j times 60 ohm. So we have to match it. Okay. For these, we have to put a matching network right in the middle. Okay. And that is what we are going to do in our Smith chart utility tool. Before that, we have to put a smart parameter, which is called smooth chart matching. Go for that. That's okay. Put it right in the middle. We haven't done with the smooth chart network yet, matching network yet. We have just put a component called smooth chart matching component. Now we have to configure this so that they're matched properly. For this, excuse me, go to Tools and click on Smooth Chart. As we mentioned before, always choose for the first option. There you go. And then according to our network, the source impedance is 50 ohm. This is our source impedance. Look at the network schematic. Just click on that thing. 50 ohms. So to prevent accidental movement, when we'll be hovering our mouses across the smooth chart, lock it so that we don't change that accidentally. And what about source impedance? Again, see, I already have put there. So it's 150 plus J60. So we have been we are just we don't change it. So we'll lock it as well. And we have to set up the frequency. Probably, I'm not sure how much is it. Maybe that's 1.5 gigahertz. So 1.5 gigahertz. A little bit of setup here. Well, 2e to the power 9, that means 2 gigahertz. So whenever you are putting something, let's say you are trying to set up your starting frequency is 1 gigahertz. Don't forget, always type 1e9. Okay, if you just press 1, if you just type 1, that's going to be problematic. So yes, so we are going to stick between 1 and 2 gigahertz, and always we measure this parameter in decibel. Our green trace is S21 and red trace is S11, and minimum value is -50, and that's it. Okay, so now let's start matching. This is really, again, just be careful. You see the lock thing has been unchecked, so again, make sure you lock it. Sometimes it might change, so I strongly recommend to check that frequently so that you don't change the load position and source position accidentally. Okay. So now let's start. So this is, again, you see these blue circles are impedance circle, and the red circles are the admittance circles. And you see that's our, you see that it's hard to say here. It's a kind of like diamond sign or rhombus. Maybe that's the load, and it's the circle. That's the source here. Source is at 50 ohm load, so that means this right in the middle of the, at the center of the circle. But load is here, so that means what do you do when you draw this smooth chart to match a circuit? You always connect this line and you find the intersection. Okay, and then so what you have to do, our intention is to make a way from here to here through those circles. So let's do that. And these are the lump elements that we will be using for our matching. So if you just click any of these, you can see. Let's choose the shunt capacitance. Just click on that thing, left click, slowly move your mouse, bring into this Smith chart area, you see something is happening here. We have done the capacitance and this is moving along the admittance circle, and as you move clockwise, you see the capacitor is having a negative value, because you know the upper half is the for the inductor and the lower half is the capacitor. So as you move and move further and go to the part below, now you are having some positive values of capacitor. So that's a shunt capacitor. That's and this is the capacitor half. Capacitor half for the capacitor values. So you have to move in a correct manner. You have to go to the lower half. This is now the right half of for the capacitor, remember. So again, you have to move this way, that means clockwise. Go. Remember, you have to reach up to this point through these circles. Okay, so well, no, you cannot reach through this circle, through this intersection. Go further. Okay, maybe you should stop here. I know whether you can, I don't know whether you can see that clearly or not, but maybe we should stop here, because there is a way that you can come through this impedance circle up to this point. So here, maybe you should stop here and see automatically the ADS has started building up that matching network for you. But this is not done yet, because we have to reach to this 50 ohm point. So now let's figure it out what actually brings you here. Let's try with the series inductor here. Okay, you see that's the circle. So maybe we are almost there. So start from here again. For the inductor, again, I need to mention one thing, that this is a impedance circle, and as you can see, this is the opposite to the capacitor. As I said, that upper half is for the inductor, so that means the value is positive, and as you go down and down, you see the negative value of the inductor, which is you have to avoid. So this is the correct manner, so that you pull in the right direction, which is clockwise in this case. And if you start from here, so that means you cannot go this way. Okay, so go here, you always see the value here is changing, the value which is in nanohenry, and come to this point and stop. We are done. There we go. So which is our way? Our point was here, which was a capacitor. That means we have to go down through the admittance circle and also the clockwise. And for the inductor, I mean, well, this is completely a perspective, but thing is that that will be really easy to understand when you just you'll be hovering your mouse, and as you can see how the value is changing. Okay, so let me show that again for you. Let's delete these things again. What if you have chosen the shunt inductor here? Let's show that. Okay, so this is the opposite thing. You can see, remember, when you have chosen the series inductor, that was a clockwise direction, but now this is a counterclockwise. So this is going to be a long way here. Maybe we should stop here, because this circle will bring us here. Okay, so we should stop here, and maybe how about choosing a shunt capacitor, maybe, well, series capacitor, you see. So we cannot do that, because we are actually losing the way here. So that's not giving us a complete circle. Rather, as you move this way, yeah, that is how we are reaching here, and that's it. So someone can say that, yeah, why not we are not moving this way? Actually, we are not going in a right direction because we are not having a complete path here. Rather, if you move this way, if you see that very closely, we are actually making a way, but we are actually not making a way here. We are losing the way here. So that's not the right way. So we have to move this way so that we can make all the way up to this point. So yes, you can say this is also a matching network. You can make this. So either way you can go. All right. So yeah, the previous one is a right approach and this one also a right approach. Okay. But still you can go anyway. So we are assuming that we have gone, we will take this way. That means we are done, and you see that is our matching network. You can see the value of capacitor, you can see the value of inductor, and you see this is the log source impedance still in 50 ohm, load impedance still in 150 plus J60. That's the S parameter. That's the S21, always opposite to the S11, and these are the value setting. We are at 1.5 gigahertz. So now that we are done with the impedance matching network, you have to click. This is really important. You have to click on that build area circuit because this is completely a different interface from what we have done here. All right. So we have to integrate that Smith chart utility or impedance match network with here. Okay. So that's why we have to choose this option here, build area circuit. There we go. And then we will click the little downward arrow here, which is called pushed into hierarchy. This is kind of cool. Now you can see clearly the matching network. Just the matching network. Don't be confused. This is not our complete circuit. This is just the matching network to have a look. What are the values? You see the C is 1.38118, which is pretty similar that what we have seen. Just a cross verification here. You see 1.38112, and then if you look at the those are gone again. The 9.22, but that's the negative side actually. Sorry, I forgot to mention that. And then L minus 9.22. Okay, well, I mean, it can be negative, but this looks like a weird value because so if you want to make it all positive, maybe you can go other way, which I have shown before this one. Okay, so yeah, normally I always prefer to choose the shortest way. Okay, so let's do that. Again, we can delete. This is still correct, but we can do in such a way so that all the values are positive. So in this way, oh, okay, again, the lock thing is gone. Make sure those are locked. So let's choose the conventional thing, which is normally series inductor. Uh, yeah. Start with shunt capacitor here. Stop here because you got a circle. You can go there as well, or you can go there even. No, I mean you can go to any circle. In that case, actually your network would be complicated because we want few lumped elements. Let me show that actually. Let's do this here. Already you have one capacitor. Okay, then maybe we can choose one inductor, or maybe we can choose one, or maybe we can choose, let's do this here. One, we have started from here. We will go this way because we are not, if you go this way, we are not having a circle. Okay, you see. So we come this way, come this way. Maybe we should stop here because that's our closest circle. Yep. And then choose one. I don't know actually, because it completely depends after selecting the component, and we will choose that component that brings us from here to here, or 50 ohm loads, 50 ohm point. So let's maybe we can try with this series inductor. Yep, we're right. So should we come this way? No, we should go this way. Can go either way. Yep, that's the positive value. So we'll go this way and come this way along this point, and there we go. So basically we got the same response, but actually we have just added another component, which is a little bit complicated uh, in terms of having only two components. Okay, so this is just for showing. Maybe we will do just with one component. So let's do that again. From here, I think that's the shortest part, and then we will go. Always remember, we will try to go so that the inductor value increases. So that's the point. There we go. We are done. Always circle in such way, either it be capacitor or it be inductor, so that your values increases. Okay, that's a trick. That's a tip actually. All right. So now we are done, and then build areas. We're done with the done looking at the network response. We're done double checking with the 1.5 gigahertz. Build area circuit here. Done. Then push hierarchy, and that's the one. We got all the positive things. See, inductor is like 8.4 nanohenry, capacitor 1.19 picofarad. This is just for looking. This is just the network to match. It's not the complete circuit. So we'll go back to the previous view, which is pop out. Now that we are done with the, okay, now where is the match network gone? This is here. This is completely linked up with that Smith chart utility. Okay, so now simulate. Okay, sorry. For these, we have to put S parameter tool. Or let's say we are going to have frequencies like what we have used here. In this case, let's say use the same 1 to 2. So we will do that, or maybe more than that. And, let's say 200 megahertz, or number of points, maybe 20 or 25, whatever. And then now that we are done this parameter setting, we should have done that before anyway, but that's fine. There we go. So we are told to look at S21 and S11. Add these things up here in decibel. Okay, there we go. Okay, so yeah, we got at 1.5 gigahertz, which is pretty good. Now let's try to verify these things with this response. Yep. Okay, so yeah, don't get confused because the ranges here is 1.122 gigahertz, whether in this case this is 1 to 5 gigahertz. So maybe we'll stop here. If you just stop here, it will look the same as you can see here. So we are done with matching between 50 ohm and 150 plus J60 ohm. Okay, you can try more if you like. So let's see what the other things here. Okay, now we're done with this part. there are some basic questions here. I have shown you these because whatever the things you are doing in your tutorial here, actually our objective is to learn this, how to match a network by using the Smith chart utility. However, we are having some really basic questions here for the sake of answering the questions for your lab report. I think you know that already. So, for example, if you want to match this network by using short circuit length or open stop length, whatever it is, whichever applies, what would happen? Let's try this. Okay. In this case, we will delete everything. Just click on that thing and select delete selected components. We are not moving from our previous load and source impedance, and we will be using this now. Okay, see the previous load point, I got the same point here. This is actually an open stop. And then how about choosing this? We can choose this, but we are not choosing here based on our prompt. We have to use only this and that icon, so that means let's choose that. Okay. So so you have to use this again. We have to use, oh, let's click on that first, and you see that's our load point. We cannot go this way because we are losing the value in terms of degree. So basically we have to go in that way where actually you will be gaining the value. So that means you're starting and you see you're gaining the value. That's the indication that you are moving in a right direction. So you have to go this way, and okay, let's stop here. How about choosing this now? So there is, well, it should come here, but actually we are not. So in this way, if we probably, because this is a, this is moving across the admittance circle, not the impedance circle. So that means it will not work. This is a open stop, and this is working along the admittance circle. So actually, we'll move this point more to a circle where it meets the admittance, immediate admittance circle, so that we can reach here. Okay, it's clearly up to you. It's really hard to tell because it varies. You can go any way so that you can reach to that point, but you have to choose always the closest one. Okay, and also you have to be watchful whether you are moving across the impedance circle or the admittance circle. Okay, so yes, now if you choose this, so now you can go this way, okay, or you can go this way, but which way you think is correct? Because if you go this way, this is not correct. As you can see that you are losing the value, so that means you have to go this way, which is clockwise. So you have started here from here, and you can see, oops, sorry, my mistake. We have to move along more. You can just drag the things also. If you accidentally stop somewhere in the middle, there you go, and that's it. So it's a mesh thing. Now when we are done, once we are done here, just double check how far you have gone. It's 126 degree. That's your, in terms of the, if you see the Smith chart, there were some distance in terms of degrees, which is 126.558 degree, and you see the BSWR is pretty close, which is 1.00294, close to 1. Once we are done, we'll look at the network response and then build areas, push hierarchy here. There we go. Back to the previous vision and simulate the thing. Okay, maybe we have to change the value here. I guess it's 1.4. So I think this answers pretty piece of cake for now, because you should be able to answer how, in which way those points are moving in terms of line length such as degree, and click on the open stop on what curve and direction. This clockwise or anti-clockwise is pretty easy to answer. I think you already know that, I guess. And based on the findings on AIB, design an open circuit stop matching network with one transmission line. Show clear screenshots from the manipulations it did on Smith chart. So we have done that already. So now we are going to see 40 to 4 gigahertz. So we have to change that frequency. Let's close this. So we have to do this from 1 to 4 or maybe 0 to 4. It's not very important to change anyway. So we are just following the tutorial, and then we'll be looking at S11 and S21. Okay, right. Looks a little bit weird, but that's fine as long as this matches with what you have seen here. It doesn't look pretty, right? Because you know the range of the frequency is here 1.2 gigahertz, whereas from here 0 to 4 gigahertz. So that means you are not seeing the whole window here. However, you can change. Let's say you want to make it 0 to 4. Remember, 4 means 4 hertz. That means you have to, this is in hertz always. So 4 times 10 to the power 9, which is 4e9. There we go. Yeah. Now, well, pretty similar here. Okay, so I think I hope you understood the things here. Maybe you can just get forward. We have to, once we are done here, let's design something else, which is a 2-element high-pass filter. In that case, we have to use, okay, this high-pass filter. That means we are having a series capacitor and a shunt inductor. And again, looking at this question, I think you know the answer already. Click on the shunt inductor. Moving in what direction results in the inductance value to increase? Pretty easy to answer. Let's start all over again. Delete these things. Let's remain there. Source and load impedance. So now, pretty easy to answer. If you just click on that thing, you know that already. You've seen that. Which way is correct? Okay. So answer the question is moving in what direction results in the inductance value to increase. So that means if you just move this way, nope, we don't see any increase. Rather, if you go this way, that's a clockwise thing. Okay. And also, since this is a shunt inductor, that means this will be on the admittance circle, completely reverse to the case of a series inductor. Okay. And on what curve are you moving as the inductance value is changing? Easy to answer, which is admittance curve. And then if you click on that thing, series capacitor, again it opposite to this shunt capacitor. So in this case, probably this would be on impedance circle. Yeah. And as you move counterclockwise, the value is increasing. Alright. So this is very easy to answer. I think you can do that. Now we will build up a 2-element high-pass filter. 2 elements. We cannot cross 2 elements. Okay. Remember, we can add 2 or 3 or 4 elements based on the distance from the, or based on the circles that we are covering. Okay, we have shown that at some points in our lab. So let's do that. So let's choose this first. sorry. Okay. Okay. So which way you should go? Nope, we are not going this way. Oh, this is actually, so yes, so we have to move this way. We are gaining the value, you can see, and moving this way, you can rotate, search for the point of intersection. Remember, this is admittance circle, so you have to find impedance circle here, or maybe impedance circle, yeah. So maybe we should stop here because there is a chance that we will go this way. So now we are done with this shunt inductor. Go to the series capacitor. It's pretty obvious. As you go, no. Should you move this way? No, because you are losing the value looking at this picofarad thing. So we have to move this way. That's the correct manner. And there we go. So yes, we are done with building up a two-element high-pass filter, and we will set the frequency range 0 to 4 gigahertz. But however, we have to look into the main circuit. For that, again, build area circuits, quotient hierarchy. That is our high pass filter. We're talking about high pass filter, right? Yeah. And we are satisfied that we have having two elements. So let's go to the previous view, 0 to 4 gigahertz, which is here already, and we will click on the simulate thing. This is coming from the probably previous simulation. So we will do that here. This one and this two one. Okay, so this is our response. Maybe the previous one is correct anyway because it auto updates the thing. However, to be on the safe side, we just we've done it afresh. Okay, so this is our response. Okay, I think we are done. So for whatever the things you have left here, that you have to answer these questions as well. So most of the things that you can see as your lab exercise questions, I think we have answered those. However, if you are still having doubts, feel free to email me. Even if someone is having struggle, maybe you can just meet me in person, and we can figure this out together. So yeah, then the last but not the least, there is a question. This question is completely up to you. Will the matching networks you design work equivalently well at 1 gigahertz, and why? So we have worked everything pretty much on 1.5 gigahertz, but this is asking whether this will be performing the same at 1 gigahertz. What do you think? And also, which of these two designs would be more suitable for working? Two design means we have used the shunt line length and open stop and short stop things, and also we have used the shunt capacitor, shunt inductor, series capacitor, the low high pass filter things. With between these matching networks, which worked better for a range of 1.5 to 4 gigahertz? Okay, I can give you a hint. Always look at the S parameter. The better the value, the better the response, the better the network. Okay, so one thing you might get at 1.5 gigahertz, which you might not get at 1 gigahertz. Okay, this could be a little worse value than what you got in the case of 1.5 gigahertz, and same goes for the S2 one. Okay, so just one thing, the more negative the S11 is better, and less negative the S21 value is better. So just looking at those values, make your judgment and have your comments. Okay, so I hope you enjoyed especially the speechability of the feature of the ADS, and it's very kind of cool feature. You can just practice on your own. And if you're having still any question, just again feel free to ask. So that's all for today. We have to see you in the next. Thank you very much. So